Okay, so let's now look at some tangent theorems. The size of the angle between a tangent and the radius is 90 degrees. It's a fairly simple idea. And if we're going to use it, I would say, well, look, OX is perpendicular to OXY, XY being the tangent that I haven't drawn in there. Reason, radius perpendicular tangent. Now, here's how I'm going to, I don't really want to call it a proof, because it's not a proof as such. It's a way of thinking about it that makes it clear why it's true. Okay, so I'm going to draw in a chord that's perpendicular to the radius. And the distance there is x from the centre. Now we know the perpendicular from the centre will always bisect the chord. So I'm going to call the length of the chord 2y. So there's y either side of that midpoint. Now if you imagine just sliding that chord along, so it's always perpendicular, the size of y will get smaller and smaller and smaller. So as x is approaching the radius, then logically the length of y would approach 0. Yeah? Look, I moved it. Y got smaller. Whoop, there we go, got smaller again. At the very end point, the length of the chord is now 0. It's no longer a chord. It's now a tangent. But it's still perpendicular to the radius. So all the way along, while I was just sliding it along and y had length, that chord remained perpendicular. The instant it touched the circumference, it was no longer a chord, it's now a tangent. But it's still perpendicular to the radius. So as I say, it's not really a proof as such, but if you think about it logically, that must happen. Fortunately, it's not something we have to prove. It's just something we can use. So we know that the radius will always be perpendicular to the tangent. All right, let's do our next one. From any external point, now we saw this with the parabola. From any external point, we can draw in two tangents. Same with the circle. There we go, my external point T. So it's possible to draw two tangents to the circle. Now what happens is, if I was to join that external point to the centre of the circle, that would become an axis of symmetry. So therefore, the length of AT would equal the length of BT. Okay. So I'm going to prove that. Let's prove that AT does indeed turn out to be the same as BT. So I'm going to join in there's three lines. So the centre up to the 3 points there. We just said that the radius will always be perpendicular to the tangent. So I know each of those triangles are right angled triangles. Radius being perpendicular to the tangent. OT is common to both triangles. And OA and OB, well, they're equal radii. So I've got congruent triangles, right angle, hypotenuse, side. And so if they are congruent, then AT must equal BT. They become the matching sides in congruent triangles. So I talked about at the start of the topic, when I talked about circles that are touching. And the two centres and the point of contact are collinear. Okay. So if I wanted to use that idea, I could say, well, look, OTH is collinear because I know the centres and the point of contact with the common tangent will be collinear. All right, let's just play with 9E, our tangents.